Welcome back to the deep dive. Look around you right now, the air you breathe, the device you're listening on, even your own body. It's all a symphony of matter and energy governed by the invisible, fundamental principles of chemistry.
It really is. We're talking about this hidden reality,
Mhm.
these incredibly tiny particles moving at just fantastic speeds, and they basically dictate how everything behaves.
And today, we're taking a foundational journey into this astonishing world. We're pulling key insights from some really solid source material on, well, the molecular nature of matter and change.
Yeah, our mission in this deep dive is really to hand you the keys to unlock this complex world. We want to go beyond just the basic definitions and show you why these concepts matter,
Right, exploring how we measure the unseen, how we manage uncertainty.
and ultimately how science itself unravels the universe's secrets. And look, this isn't just for future chemists or scientists. It's crucial for anyone who wants to be truly well-informed about the physical world around them.
Exactly. We're here to guide you to those, aha moments.
Let's hope so.
Okay, so let's unpack the very essence of what chemistry studies. We know it's the scientific study of matter and its properties, how it changes, and the energy tied to those changes. But what really is matter in a chemist's eye?
Well, at its core, matter is basically anything that has mass and volume.
Simple enough, right?
Yeah.
The air, your phone, planets, us.
Exactly. But, not all matter is created equal, chemically speaking. When we talk about a substance, we're getting more specific. We mean a type of matter with a defined, fixed composition.
Like pure gold, maybe? Or distilled water?
Precisely. That consistent, unchanging identity is what allows chemists to predict its behavior, build reliable models, that sort of thing.
Okay. And matter, as we all observe, comes in different physical forms. Solids, liquids, gases. We see that every day.
We do. But for chemists, the real story isn't just those visible forms. It's about how the underlying particles, the atoms and molecules, dictate those behaviors.
Right. The microscopic dictates the macroscopic.
Exactly. So in a solid, you picture those particles packed really tightly, often in a rigid, ordered pattern, like soldiers in formation.
Okay.
In a liquid, they're still close, bumping shoulders, but they're tumbling and sliding past each other. Much more freedom.
More fluid, literally.
Right. And in a gas, well, they've pretty much broken free. They're zipping around randomly with huge distances between them, filling whatever container they're in, no surface, just everywhere.
So this brings us to a really core idea, doesn't it? What we actually see and observe at our scale, the macroscopic scale.
Yeah, the visible properties, the behavior of stuff.
It's all a direct result of how things are behaving at the atomic scale, which we can't see directly.
That's the crucial link. Our study of observable changes helps us understand their unobservable causes. It's like being a detective, piecing together clues from the visible world to understand the hidden one.
I like that analogy. And we learn about matter by looking at its properties and the changes it undergoes. So let's talk about physical properties.
Okay. These are characteristics a substance shows just by itself, without changing what it fundamentally is. Think color, melting point, density, electroconductivity. Things you can measure without altering its chemical identity.
And a physical change follows from that, right? It's when those properties shift, but the substance itself stays chemically the same.
Absolutely. When ice melts to water, it looks different, feels different, but it's still H2O. The molecules are just arranged differently. All changes of state, melting, boiling, freezing, are physical changes.
Got it. But then there are chemical properties.
Right. And these are characteristics that only really show up when a substance changes into or interacts with another substance. Think flammability. You only know wood is flammable when you try to burn it, changing it into ash and gases. Or corrosiveness.
Okay, so that leads directly to chemical change, or what we usually call a chemical reaction.
Exactly. That's the transformation itself. One or more substances are converted into one or more new substances with different compositions and completely different properties.
So the crucial difference is whether the substance's core identity, its actual molecular makeup, changes. That's the key, isn't it?
That is absolutely the key. Think of it like, well, imagine Lego bricks. A physical change is just moving your pre-built Lego car around, maybe dusting it off. It's still the same car.
Okay.
But a chemical change, that's like taking the car apart and using those same bricks to build a completely new Lego spaceship. Same basic building blocks, but a fundamentally new creation with totally new properties.
That's a great way to put it. Like passing electricity through water, you don't have water anymore.
No, you get hydrogen gas and oxygen gas. Completely new substances. And importantly, unlike melting ice, which you can easily reverse by freezing it again.
Right.
Most chemical changes aren't simply reversible just by cooling or heating. You usually need another chemical reaction to get back, if you even can.
So what's fascinating here is that ultimately all these changes, physical or chemical, boil down to energy shifts, don't they?
They absolutely do. Everything in the universe, from a star collapsing to a cell dividing, involves energy changing form. Energy, simply put, is the ability to do work.
And we need to understand its different forms, like potential energy.
Yeah, the stored energy. Think of a stretched rubber band, or water held back by a dam, or even the energy stored in chemical bonds. It's energy due to position or composition. It's often less stable.
And the other main form is kinetic energy.
Right, the energy of motion. When you release that rubber band or the water flows over the dam, that stored potential energy converts into kinetic energy. Systems naturally tend to move towards lower potential energy, towards more stable states.
And in chemistry, we talk specifically about chemical potential energy.
Exactly. It arises from the relative positions of atoms and the strength of the bonds connecting them within a substance. Think about gasoline and oxygen. They have a lot of stored chemical potential energy.
And when they react in an engine?
That energy is released, converted largely into kinetic energy, the motion that moves the car, and also heat. But the critical insight here, the fundamental law, is that energy is always conserved.
It just changes forms?
It just changes forms, usually moving from a state of higher, less stable potential energy to a lower, more stable state. That drive towards stability powers pretty much everything.
Okay, so if the world is built from these hidden particles and driven by these energy transformations, how do we, as scientists, even begin to figure this all out? How do we go from just watching something happen, like a candle burning, to understanding combustion at the molecular level?
That's where the scientific method comes in. And it's really important to understand it's not some rigid step-by-step instruction manual you follow blindly.
Right, it's more dynamic.
Much more. It's an iterative process of discovery, a way of thinking, a playbook for replacing guesswork and speculation with verifiable, reliable knowledge.
Okay, so what are the key elements of this playbook?
Well, it always starts with observations. These are the facts, the data we gather about the world that our ideas must explain. And quantitative observations, the ones involving numbers and measurements, are usually the most powerful.
Why is that?
Because numbers can reveal trends and relationships that simple descriptions might miss. And when observations are found to be universally consistent, like they happen the same way every single time under the same conditions, they can sometimes be summarized as a natural law.
Like the law of mass conservation, matter isn't created or destroyed in a reaction.
Exactly. That came from countless careful observations. Yeah. But just observing isn't enough, right? We want to know why.
So we propose an explanation.
Precisely. We form a hypothesis. This is a tentative proposal, an educated guess, designed to explain the observation. The crucial thing about a hypothesis isn't whether it's right or wrong initially.
It's whether it's testable.
It must be testable, usually through an experiment. An experiment is a set of controlled steps designed specifically to test that hypothesis. A good experiment tries to isolate variables changing one thing while keeping others constant to see its effect.
And the results need to be reproducible, right? Someone else should be able to do the same experiment and get the same outcome.
Absolutely critical. Reproducibility is the cornerstone of reliable science. If experiments consistently support a hypothesis, it gains strength. If they don't, the hypothesis has to be revised, or maybe even thrown out completely.
Okay, so observations lead to hypotheses, which are tested by experiments. What comes next?
Well, as hypotheses get refined and are consistently supported by lots of reproducible experimental evidence, a conceptual model or theory starts to emerge.
So a theory isn't just a guess, like we sometimes use the word?
Not in science, no. A scientific theory is a well-substantiated, comprehensive explanation of some aspect of nature. It's built on a large body of evidence. It's a simplified but powerful representation used to explain why phenomena happen and even predict new related phenomena.
And theories aren't set in stone either, are they?
Definitely not. They're our best current understanding, but they're always open to refinement, modification, or even replacement if new, compelling evidence comes along. Science is self-correcting.
That whole process is really well illustrated by Antoine Lavoisier's work on combustion back in the 18th century, isn't it?
Oh, it's a fantastic example. Before Lavoisier, the dominant idea about burning was this thing called phlogiston.
Right, this mysterious substance that was supposedly lost when something burned. Sounds a bit, well, mystical now.
It does. But it was the accepted theory for a long time. People observed things burning and getting lighter, seemingly losing something. But Lavoisier wasn't satisfied. He brought quantitative rigor, careful measurement to the problem.
What did he find?
He meticulously weighed reactants and products. He noticed that air was absolutely required for burning. And crucially, when metals blend, like rusting, a slow combustion, they actually gained mass. They didn't lose it.
That completely contradicts the phlogiston idea.
Totally. So his observations led to a new hypothesis. Combustion wasn't about losing phlogiston. It was about combining with a component of the air. He later identified this component as oxygen.
And this wasn't just a new guess, it became a powerful model.
Exactly. His oxygen theory not only explained burning metals, but also things like candles burning and even animal respiration breathing. It showed how the scientific approach, grounded in careful, quantitative observation and testable hypotheses, could replace centuries of speculation with a deep, verifiable understanding. That shift to measurement was key.
That quantitative rigor really does seem central. If we're going to rely on measurements and data, we need a consistent way to talk about them, a common language.
Absolutely. Understanding what to study and how to study it is only part of the picture. We need a universal language for quantifying our observations.
Wow.
And that brings us to the power of measurement in units.
Because standards used to be all over the place, right? Like based on a king's foot or something?
Pretty much. Measurement standards were incredibly variable. Think about trying to reproduce an experiment if a handful was the unit of mass. It was chaotic. The metric system, developed in France actually with input from Lavoisier,
Ah, makes sense.
and later refined into the universally accepted SI units, the system International d'Unité, brought that desperately needed standardization.
Yeah.
It's based on fundamental, unchanging physical quantities.
And the beauty of the SI system is its coherence, isn't it?
Yes, it's built on 7 base units:
Yeah.
the meter for length, the kilogram for mass, the second for time, the Kelvin for temperature, and a few others. All other units we use are derived units, which are just combinations of these base units.
Like speed being meters divided by seconds.
Exactly. Or volume being lengths cubed.
Yeah.
And importantly, the whole system is decimal-based. We use prefixes like kilo, meaning 1,000 times larger, milli, 11,000th, micromillionth, nanobillionth.
Which makes calculations so much easier than, say, converting inches to feet to miles.
Oh, infinitely easier. Working with powers of 10 using exponential or scientific notation is incredibly efficient, especially in chemistry where we deal with both astronomically large numbers of atoms and incredibly tiny distances.
Speaking of tiny distances, while the meter M is the base unit for length, chemists often work at much smaller scales.
We do. We often use nanometers, nm, which are billionths of a meter, to talk about the size of large molecules like proteins, or even smaller, picometers, pm, trillionths of a meter, for the diameters of individual atoms. You might still see the older unit, the angstrom. Sometimes, too, it's a tenth of a nanometer.
And for volume, the SI unit is cubic meters, but that's huge for lab work.
It is. So while m is the official derived unit, chemists almost always use the liter, L, and the milliliter, ml. It's just more convenient. Remember, 1 liter is the same volume as a cubic decimeter, DMO, and 1 milliliter is exactly the same as a cubic centimeter, CMO or CC.
Okay, got it. And mass, the SI unit is the kilogram cubal.
Yes, the kilogram. And it's really important here to distinguish mass from weight. Mass is the actual amount of matter in an object. It's constant no matter where you are.
Whereas weight depends on gravity. You weigh less on the moon.
Exactly. Weight is the force gravity exerts on an object's mass. Those balances we use in the chemistry lab. They're designed to measure mass, usually by comparing the unknown mass to known standard masses, effectively canceling out gravity's effect.
Right. And every measured quantity needs both a number and a unit, doesn't it? Just saying 5 doesn't mean anything. 5 grams, 5 meters, 5 liters.
Precisely. The unit gives the number its meaning, and often we need to convert between units. For that, we use conversion factors.
Which are just ratios of equivalent quantities, like 1 inch equals 2.54 centimeters.
Exactly. Since those two quantities are equal, the ratio, like 2.54 centimeters, 1 inch, or 1 inch, 2.54 centimeters, essentially equals 1. So when you multiply your measurement by the right conversion factor, you change the units but not the actual physical quantity.
You choose the factor that makes the old unit cancel out, leaving the new unit you want.
That's the core idea of the factor label method, or dimensional analysis. It's a really powerful way to guide your calculations and make sure your answer has the right units. It helps prevent simple mistakes.
This all ties into a systematic approach to problem solving, which seems crucial in chemistry. It's not just about plugging numbers into formulas.
Absolutely not. The textbook emphasizes a clear method, and it's good practice. First, you plan. Understand the problem. Identify what you know and what you need to find. Maybe sketch out a roadmap of the steps and conversions needed.
Okay, plan first, then.
Then the solution. Carry out the calculations using dimensional analysis to keep track of units.
And you're not done yet.
No way. You have to check your answer. Do the units make sense? Is the magnitude reasonable? Does it feel right based on your understanding? A quick ballpark estimate beforehand can be really helpful here.
That checking step sounds vital. Avoid silly errors.
It really does. And finally, practice. Follow-up problems help solidify the concepts. It's about building reasoning skills, not just getting the answer.
Okay, let's touch on a key derived unit. Density.
Ah, yes, density. Super important. It's defined simply as mass divided by volume. D equals mv.
Yeah.
Its SI unit is kilogmneo, but in the lab, we typically use GML for liquids and solids, or maybe GL for gases.
And density is an intensive property, right? It doesn't depend on how much stuff you have.
Exactly. A drop of water has the same density as a swimming pool full of water, at the same temperature, of course. This makes it incredibly useful for identifying substances. Gases, by the way, have much, much lower densities than liquids or solids because their particles are so far apart.
And speaking of temperature, let's clarify that. It's related to heat, but not the same thing.
Good distinction. Temperature T is a measure of how hot or cold something is relative to something else. It reflects the average kinetic energy of the particles in the substance. Heat, on the other hand, is the energy that actually flows between objects because of a temperature difference, always from the hotter object to the colder one.
Okay. And we use different scales to measure temperature.
We mainly use three: Celsius, degrees, common worldwide, where water freezes at 0 degrees C and boils at 100 degrees C. Then there's Fahrenheit, degrees F, primarily used in the US, with water freezing at 32 degrees F and boiling at 212 degrees F.
And the SI unit.
The Kelvin K scale. This is the absolute temperature scale. It uses the same size degrees as Celsius, but its 0 point is absolute zero, 0 K, the theoretical lowest possible temperature where particle motion is minimal.
Which is about negative 273.15 degrees C.
Exactly. So to convert Celsius to Kelvin, you just add 273.15 TK, PLT, degrees C, plus 273.15. And notice we don't use a degree symbol with Kelvin. It's just K. This scale is fundamental in many scientific calculations, especially those involving gases.
This brings us back nicely to that distinction between extensive and intensive properties. We mentioned density is intensive.
Right. So extensive properties depend on the amount of substance you have. Mass is extensive, more substance, more mass. Volume is extensive, the total heat energy in something is extensive.
But intensive properties are independent of the amount.
Correct. Density, temperature, color, melting point, boiling point. These are characteristic of the substance itself, regardless of whether you have a tiny speck or a huge chunk.
Like our copper cube example, a small one and a big one have different masses and volumes, extensive, but the same density and melting point, intensive.
Exactly. Intensive properties are super useful for identifying unknown substances because they're consistent.
Okay, we've covered what we study, how we study it, and how we measure it. But there's a catch, right? Every measurement has some fuzziness.
Absolutely. No measurement is perfectly exact. Every measuring device, whether it's a ruler, a graduated cylinder, or a sophisticated instrument, has limitations. And we as humans reading the device always have to estimate the last digit. This inherent limitation is called uncertainty.
So how do we deal with that? How do we report our measurements honestly?
We use significant figures, or sig figs. These are the digits we record in a measurement, all the digits we know for sure, plus one final digit that we've estimated.
So the number of significant figures tells you something about the certainty of the measurement.
Precisely. More significant figures mean a more precise measurement, greater certainty. Fewer sig figs mean less certainty. It's our way of communicating the reliability of our data.
Okay, but determining which digits are significant can be tricky, especially with zeros.
It can seem that way, but there are clear rules. All non-zero digits are always significant. Zeros between non-zero digits are always significant. Like in 502, the zero counts.
What about zeros at the beginning or end?
Leading zeros, the ones at the beginning of a number less than 1, like in 0.0055, are never significant. They just locate the decimal point. That number only has 2 sig figs, the 5s.
Okay, and trailing zeros, the ones at the end.
Trailing zeros are significant if the number has a decimal point explicitly written. So 1.1300 have 5 sig figs. Those zeros indicate the measurement was precise to that level. 0.000350 has 3 sig figs.
What if there's no decimal point, like in 5300?
That's ambiguous. Does it mean 5300 exactly or just roughly 5300? Typically, we'd assume only the 5 and 3 are significant, 2 sig figs. The best way to remove ambiguity is to use scientific notation.
Right. 5.3 by 10 in miracles clearly has 2 sig figs, while 5.300 by 10 in ovals clearly has 4.
Exactly. Scientific notation makes the significance of trailing zeros crystal clear.
So that's how we report a single measurement. But what happens when we use these uncertain measurements in calculations, like multiplying or adding them?
Great question. The fundamental rule is that the result of a calculation can't be more certain than the least certain measurement you use to get it. Your answer's precision is limited by your weakest link.
Okay, how does that work in practice?
For multiplication and division, the rule is simple. Your answer should have the same number of significant figures as the measurement with the fewest significant figures going into the calculation.
Got it. Fewest sig figs limits the answer sig figs. What about addition and subtraction?
It's slightly different for addition and subtraction.
Right.
Here you look at the number of decimal places. Your answer should have the same number of decimal places as the measurement with the fewest decimal places.
Okay, decimal places for skizzen, sig figs for x, and we need to round our answers correctly.
Yes. Standard rounding rules apply. If the digit you're removing is 5 or greater, round the preceding digit up. If it's less than 5, leave the preceding digit as it is.
What about exactly 5?
The common convention, especially in science, is if the digit to be removed is exactly 5, with nothing after it or only zeros, you round the preceding digit to the nearest even number. This helps avoid systematic bias in rounding over many calculations. And a pro tip, carry extra digits through intermediate steps in a multi-step calculation and only round the final answer.
Good tip. Are there any numbers that don't have uncertainty?
Yes, exact numbers. These have infinite significant figures, effectively. They come from definitions like 60 seconds in 1 minute or 1,000 grams in 1 kilogram, or from counting discrete objects like 3 beakers. They never limit the number of sig figs in your calculation.
Okay, this all ties into making sure our data is reliable. We also hear terms like precision and accuracy. Are they the same thing?
No, they're definitely not, and the distinction is crucial. Precision refers to how close multiple measurements of the same thing are to each other. It's about reproducibility. High precision means your measurements are tightly clustered. Low precision means they're scattered all over the place. It relates to a random error.
Okay, so precision is about consistency among measurements. What's accuracy?
Accuracy refers to how close your measurements are to the actual or true value. High accuracy means your measurements are, on average, hitting the correct mark. Low accuracy means your measurements are consistently off target. This relates to systematic error.
Can you give us that target analogy again?
Sure. Imagine shooting arrows at a target. If all your arrows hit very close together, that's high precision.
Even if they're all clustered in the top left corner, away from the bullseye.
Yes. That'd be high precision, but low accuracy. You have a systematic error. Maybe your sight is misaligned.
Okay. And if your arrows are scattered all over the target, but their average position is right on the bullseye?
That would be low precision, high random error, but potentially high accuracy on average. Ideally, of course, you want both. High precision and high accuracy, all your arrows clustered tightly right in the bullseye.
So how do we fix low accuracy, that systematic error?
That's where calibration comes in. We compare our measuring device, whether it's a balance, a thermometer, a pH meter, to a known, trusted standard, and we adjust the instrument so it reads correctly. It's like zeroing your bathroom scale or adjusting the sight on your bow. It minimizes systematic error.
Wow, okay. That covers a huge amount of ground, but really essential stuff for understanding how chemistry works.
It really is the foundation.
And that brings us pretty much to the end of our deep dive into these foundational keys of chemistry.
I feel like we covered a lot.
We definitely did. So let's recap the big takeaways. We started by seeing chemistry absolutely everywhere, didn't we? From the tiniest particles to the products we use every single day. Matter and energy are the fundamental players.
Yeah, and a key idea is understanding how matter states, solid, liquid, gas, and its changes, both physical and chemical, really involve bridging that gap between what we see, the macroscopic, and what's actually going on unseen at the atomic and molecular level.
And we saw that the scientific method isn't just a rigid recipe, but a dynamic, iterative way to build reliable knowledge. It relies on those testable hypotheses and, crucially, reproducible experiments.
That reproducibility is key. And the language we use to describe our findings, the language of measurement, demands precision. That comes through agreed-upon standards like SI units and using a systematic approach to calculations and problem-solving, like dimensional analysis.
Right. And finally, we tackled uncertainty, recognizing that every measurement has limits and managing that uncertainty through concepts like significant figures, understanding the difference between precision and accuracy, and calibrating our instruments. That's all absolutely crucial for generating trustworthy results in any scientific field.
You can't have reliable science without acknowledging and handling uncertainty properly.
So the source material started by showing chemistry in everyday life. Now that you, listening, have got these essential keys to studying it, the concepts, the method, the language, the approach to uncertainty, here's something to think about.
How will you look at the everyday stuff around you differently now? Knowing about that invisible world of particles and energy shaping its properties and behavior.
And appreciating the careful, rigorous methods scientists use to understand it all.
It really can make the ordinary seem quite extraordinary, can't it?
It absolutely can. That's the beauty of it.
Well, thank you so much for joining us on this deep dive.
Always a pleasure.
Until next time, keep exploring, keep questioning, and keep being brilliantly curious.